Okay, welcome again to the lecture course on Relativity and Cosmology Part 1. We are doing gravitational waves, and we have so far studied the propagation of the waves in vacuum. They propagate with the speed of light, and they have a transversal polarization as in electrodynamics, but the polarization axis is different, so they are inclined with respect to each other by 45 degrees, not by 90 degrees. So there are two independent polarization states called plus and cross polarization. Now, of course, what is of important interest is how do you generate these gravitational waves? I mean, they must come from somewhere. And this is the content of this important section 7.3. So let us first have a look at electrodynamics, and let us use Gaussian units for that. There, an important special case is the emission of dipole radiation. So, emission of dipole radiation. And if you assume that the source, I mean the charges, move non-relativistically, then we have this important result for the emitted power, dp over the omega. So this is the power, and this is the spherical angle omega is, and I take the speed of light into account, c times d double dot squared sine squared theta over 8 pi, where d is the dipole moment, which is defined integral over x times the charge density. Now this should be known to you. So if we have here, say, the dipole vector d, then you have the emission, and this is so-called Hertz dipole, that you have the emission here that follows this law. So it's roughly has like that. And of course you can see the exact appearance in the books, but roughly it's like that. So you have here this angle theta, which is here. So we have here no emission in the direction, but we have here emission in this other directions. In general, what you do in electrodynamics is, of course, to make a multipole expansion. I mean, the source may be somewhat complicated, but localized, and not just a dipole, which you can imagine of this linear antenna. So you have then the next order quadrupole and octupole and so on. So the next order in still electrodynamics, next order is then the quadrupole radiation, which has also a result that maybe is not so discussed usually in detail, but you can find it in standard text of electrodynamics. And it has this expression. So instead of the dipole vector, you have a quadrupole tensor. So sum of KL is 1 to 3, QKL, QKL, and instead of the second time derivative, you have here the third time derivative. So if you go to Fourier space and Fourier transform, then you get a result. Instead of the 3 time derivatives, you get an omega cube. So this gives you an omega to the 6. So you get c times omega to the 6 over 40. And you have the sum of KL is 1 to 3. And you have here the Fourier components of the Q's. Yeah, so I should, of course, say here, this here, the total power, which is the integral over this differential emission, gives you c over 3 d double dot squared, which in Fourier space corresponds to c over 3 omega to the 4th d omega squared, where this is the Fourier transform of this, and you see here the difference in power that you have here. So you have here the well-known omega to the 4 factor that is responsible for the blue appearance of the sky, and here in quadrupole approximation or quadrupole rotation you have omega to the 6. Now let me remind you also how the quadrupole tensor is defined. So you have here Q, KL is integral d3x, and okay, here you have one x and there you have two x's, and this is why it gives a tensor. And so one definition is this here. No, this is just the Euclidean distance r. Now sometimes you define it without that second term, just with the first term, so that depends on whether you want it to be traceless or not. Sometimes it's convenient to have a traceless when you have the form of trace, which means here the trace of this is 3, so this would then be r squared minus r squared 0, but sometimes you just have this definition. So be careful when reading literature. What is the convention for the quadrupole tensor? Now, so far electrodynamics. What about gravity? Maybe we just have the same situation. We have a dipole and a quadrupole and so on. So let us have a closer look. So in gravity, then you would have a dipole moment d, which is integral d3x, x times rho, and this is now the mass density. No? Here you have the charge density, and here you have the mass density. So for n particles, say, then we have just a sum. So this is for continuous mass density, and for n particles you just have here a sum k equals 1 to n mk xk. Now that would be the expression in the discrete case. So if you had an analogous expression here, we have the second time derivative, then also you would expect this here. So the first time derivative here is the sum of k equals 1 to n mk xk dot, but these are just the momenta of the particles. So this is the total momentum. So if you have another time derivative, then you get the derivative of the momenta. But if you have no external forces, and here we have of course a closed system, then momentum is conserved. So this is 0. So we would not, from this argument, we would not expect dipole radiation to exist for gravitational waves. And this argument here really holds. We shall see when we calculate the exact result. You will see that there is no contribution from the dipole, and that the first contribution actually comes from the quadrupole. No? So expect absence of dipole radiation in GR. No? And in fact, it turns out, and you will see that in the following, that the first non-vanishing contribution will be the quadrupole contribution. So the first non-vanishing contribution will be quadrupole radiation. And you see here from electrodynamics, you have the term q triple dot squared, and in fact we will also find such a term, of course with a different prefactor. No? So we will find, and this is what I shall derive in the following, with the same as there, but with a factor g over 5 c to the 5 instead of c over 40 for electrodynamics. So in order to calculate the emission of gravitational waves from a source, we have to solve the linearized Einstein equation. D'Alembert phi mu nu is minus 8 pi g t mu nu, where t mu nu is the energy momentum tensor of the source, which you will see typically moving compact objects moving around each other. Phi is the rescaled perturbation of the metric. I mean, the metric is close to the flat metric. There's a small perturbation psi, and this phi is a redefined version obeying the harmonic condition such that this equation is simple. No? Otherwise, you would have here a more complicated term. Now, this equation, or the structure of such an equation, is very well known to you, because you have encountered such an equation in electrodynamics for the vector potential, for example. It's an inhomogeneous wave equation, and you have studied in electrodynamics the methods how to solve this. And the standard method is the method of Green functions. More precisely, the retarded Green functions. So if you recall electrodynamics, there we use the retarded Green function for the solution. Now the retarded Green function has the following defining properties. It obeys a distributional wave equation in the form d'Alembert retarded Green function depending on x minus x prime. So this stands for the four-dimensional coordinates, is the four-dimensional delta function. And the four-dimensional delta function we write as the product of the time part and the three-dimensional spatial part. And the retarded, of course, means that it's zero for this time difference t minus t prime negative. So the initial condition is that the G retarded is zero for t minus t prime negative. Both electrodynamics and also gravity is time reversal invariant. So you have so-called retarded and advanced solutions, and we choose the retarded ones because they obey to our principle of causality, that you first have the excitation of the source and then you have, say, the propagation. The time reversal would be to have first the propagation and then the effect on the source, which we will not consider here. I will also not repeat the solution of this equation. I mean, it's standard, and you can check your favorite textbook or notes on electrodynamics for that. So the solution of this is, well, of these two, is that the G retarded is 1 over 4 pi x minus x prime. And then you have the delta function of t minus t prime minus x prime absolute over c. So for illustration, I put the speed of light here explicitly. And for the retarded, I have here the theta function, which is 1 for argument positive, but vanishes for argument negative. So the situation we have in mind is the following. I mean, now for gravity, no? And we want to do the similar thing here. So we have the following picture in mind. We have a source, a matter distribution, so this can be just one asymmetric body, but it can be many bodies, and typically is, that circle around each other. So one example later will be two black holes circling around each other and emitting gravitational waves. So this is the source, and so we are here, and so we have some origin that is within the source, and we denote this here as the vector x, and here this as the vector x prime. So x prime will vary across the source here, and this here then apparently is x minus x prime, and I call this r. So this here, the absolute value of this is r. The solution of such an inhomogeneous equation, if you have the correspondent Green function ready, is the convolution integral of the Green function with the source. That's what is the big advantage of this, because once you have this Green function at your disposal, you can write a formal solution of this for any inhomogeneity. No? So the formal solution of that is that phi mu nu retarded of x, and x means, of course, x and t, x vector and t is then the integral d for x prime. No, this is about on this around the region of the source of minus 8 pi g t mu nu of x prime g retarded of x minus x prime. So if I insert this here and if I perform the temporal integration, so I get rid of this green function, of this delta function here. So I am left with, so after having the t prime integration, that we have here minus 2g, and we have the integral over the source d3x prime, and we have then the t mu nu of x prime t minus r over r. So that would be then the formal expression that we get. Of course, in general, this t mu nu is so complicated, so you cannot expect that you can exactly evaluate this integral. What you do in general is to apply a method known from electrodynamics, and this is called the multipole expansion, and this is also what we shall apply here. Just a remark, here we have this gauge condition here that of course must be fulfilled. So is the divergence of the left hand side 0? Well, it's 0 if the ordinary divergence of t mu nu is 0. And this in fact holds because we are here in the linearized regime, so there's no back action of the wave on the source, and this is why we have ordinary conservation, energy momentum conservation of the source itself, and not the covariant conservation as the full theory demands. So this is consistently implemented. Now we are far away from the source, and this is meant in a literal sense, because typically these are events light years, if not millions of light years away. So this is an excellent approximation. So we are far away from the sources, and so we said r is approximately equal to absolute value of x, because this difference here are negligible compared to the distance to the observer here. Here we have the observer. And this is of course what we call the radiation zone. Yeah, if the extension of the source does not matter if you are far away. We can then write from this that this is approximately minus 2g over r. So this r can then be put outside the integral, and we have integral d3x prime t mu nu of x prime and t minus x. I should mention another point, of course, this approximation here, which is very crucial. For this to hold, we must have, of course, this, but also something more. We must also assume that the wavelength of the wave is much bigger than the extension of the source. Why? Because also here, in the argument of t mu nu, we have an x minus x prime here hidden, and we substitute this by just x, and this we can only do if the wavelength does not vary very much along the source. No? I mean, this t mu nu, they may contain terms, for example, like cosine omega t minus x minus x prime. Think terms like that are typically here, and this omega is 2 pi over lambda. So lambda must be much bigger than this, so that we can neglect this here. You know, so lambda must be much bigger than the extension of the source. Well, I mean, there may be situations where this does not hold, and in these other situations, of course, you must go to a more detailed analysis. Now, how do we further modify this so that we can apply the multipole expansion? There is a rather well-known theorem called the Laue theorem, named after Max von Laue, who proved already in special relativity, and in a sense we are concerning the background in special relativity, that relates the integral over certain components of t with their second time derivatives. And this Laue theorem will be applied here. So there is the Laue theorem, and it says that the spatial integral over t kl, so these are the spatial components, is 1/2 d squared over dt squared integral d3x t00 times xk times xl, and the t00 is the energy density rho. No, so that's the theorem. I will not prove it here in the lecture course. You find it in many sources. I think it's in Hartel's book, if I'm not mistaken. If you like it to learn a little bit more about this, there's a nice article by Giulini, which you may wish to read, although it's not needed for what follows, on the archive. So it's 1808 0932. So that's something that Laue, I mean, before the advent of general relativity, proved in special relativity, but because of the linear approximation, we can use it here. No? So you already see here the emergence of these time derivatives of the energy density, which will then later give the emitted power, and you see here the spatial coordinates occurring twice will then later be put together for the quadrupole tensor. And as I mentioned earlier, there is no dipole radiation in gravity, but there is quadrupole radiation, and this you will see here by applying this theorem. So let me use this. So we have, let me write it down again, the phi mu nu, and I will skip the retarded. So all the quantities that are written down are for the retarded solutions. So phi mu nu of x and t, we had is minus 2g over r integral d3 x prime t mu nu of x prime and t minus x. So to apply this, we just formulate this for the spatial components. I will tell you later how you will get the remaining components of x and t is approximately 2. Okay, this is just copied, and then we use now here for this Laue theorem. Here, that's this left hand side is here then replaced by the right hand side, and this is minus g over r. So the factor 2 goes away by the 1/2, and we have the integral d3 x prime rho double dot xi prime xj prime. So that's the important expression here now that follows after the Laue theorem has been applied. And of course the rho has to be evaluated at retarded time. So you see explicitly from the occurrence of these two that there is no dipole radiation, as we have argued earlier by using momentum conservation, that in contrast to electrodynamics there is no and cannot be dipole radiation. You see also the formalism gives us this result, as the formalism should, of course. Now the remaining components of phi you get by applying here our harmonic condition, because we have now the spatial components, and if we set mu here is equal to I and mu equal to 0, we get a remaining component. So we have from phi mu nu equal to 0, we have mu equal to I, we have phi I0 dot is minus phi ij comma j. So if you have these from here, you can calculate the phi I0, and by setting mu equals 0, I have then phi 0 0 comma 0 plus phi 0 I comma I 0. So you have now these, and you get the remaining phi 0 0. No, so there is no loss of information about the phi mu nu. Now next we calculate the energy flux for the propagation in x direction. Recall, as a particular example, I chose the x direction, so I have the energy flux for the propagation, or for propagation in x direction. Assuming that far away from the source, we can assume that the wave has the form of a plane wave, which is a good approximation. So we called this flux fx. I mean, this was the component T01, gravitational wave. And the expression was or is as follows. I will say again where it follows from. So it's formulated with respect to the original field psi. So this is what follows, as I said earlier, from the canonical energy momentum tensor, that follows from the Einstein-Hilbert action in the linear approximation. No? You have the Einstein-Hilbert action, you make this ansatz here, so you get something quadratic in psi, and you use the standard formula for the canonical energy momentum tensor to get the corresponding components. Recall, this is when you do the average. This is what gives you what I had earlier in section 7.2, this over many wavelengths, this flux or energy density omega squared amplitude squared over 32 pi g. Now here I have the result for phi mu nu. Of course we need the result for psi. So which you get from here by just inverting this, and by performing the trace you can substitute this by the trace of phi. So we use phi mu nu is psi mu nu minus 1/2 eta mu nu psi rho rho. And what you get here in particular is that for this case that psi 22 minus psi 33 is the same as phi 22 minus phi 33, so they coincide, and also the components psi 23 is the same as phi 23. So those components, they coincide, so I can use here directly this here to get this. So I have phi 22 minus phi 33 is by using this here is minus g over r, and we have the integral dx prime rho double dot x2 prime squared minus x3 prime squared. And recalling the definition of the quadrupole tensor, we can rewrite it as follows. So let me give you again for you what I had earlier, the definition of the quadrupole tensor, which is integral d3x xi xj minus 1/3 delta ij r squared times rho. I mean, this was the definition I use and will use in the following, which gives you a trace-free quadrupole tensor because of that term. As I said, other authors skip that and have another definition, and then you get, of course, different results. So you see here, this is what appears here. No? So you have here x2 prime squared. So this gives a q together with rho proportional to q22, and because of the double dot gives you q2 double dot. So this here then is minus g over r, and you have q22 double dot minus q33 double dot. And the same, okay, and you see here we have here this difference here, and also the psi 23 here is the phi 23 here. So for this expression fx, you then get the following in terms of the quadrupole tensor: 1 over 4 pi g, and you have g over r squared. And then you get the quadrupole tensor terms, which is 1/4 q22 triple dot, no? Because you have here another dot, and you have here in the phi's you have double dot. So all in all, you get a third derivative of the quadrupole tensor, the third derivative. This is important. Minus q33 triple dot squared plus q23 triple dot squared is g over 8 pi, that is just together 8 pi r squared. So you have a 1 over r squared here in front, and you get here 2 q23 triple dot squared plus 1/2 q22 triple dot minus q33 triple dot squared. So this I have chosen for convenience, this factoring out of numbers. It's more convenient for what follows. So this is for a wave propagating in x direction. Of course, we would like to have a general expression for the propagation in any direction, say the direction given by a normal vector 1, 0, 0. And this is what I shall do next. So we now want to generalize the expressions done for the x direction to an arbitrary direction. And the arbitrary direction is here specified by a unit vector n, that here we have just 1, 0, 0. No? In a spatial vector, so in our particular case it would be the x direction, but later we want to formulate it with general n. So this is the unit vector in direction of propagation. Let me define a matrix, a 2 times 2 matrix, Q, T, with the components Q22, Q3, Q23, Q23, so a symmetric matrix that in a sense is transversal to n, which is here entirely defined in the YZ plane, and let me define a transverse traceless version of that. That reminds, of course, a transverse traceless gauge, which is Q2 times 2 trace, in that we subtract the trace of this. And so we subtract minus 1/2 Q22 plus Q33 1, 0, 0, 1. So it's clear if you calculate the trace of this, then you get 0. Okay, if you write it down explicitly, it's 1/2 Q22 minus Q33, Q23 minus 1/2 Q22 minus Q33. Now next we want to calculate the following. We take this and calculate the trace of the quadratic form QTT, and okay, that's easily done. I mean, you have a 2 times 2 matrix, and you make the multiplication with itself, and you calculate the trace, and you find that this is 2Q23 squared plus 1/2 Q22 minus Q33 squared. Why do I do that? Okay, it will become fully clear in a minute, but perhaps you can recognize that this has a similar form than the expression I had written down earlier for the flux, just that you have here not yet derivatives on the Q. No? And I do this because that was the particular combination for the x direction, and this formalism then will be generalized to any direction. No? So if I have any direction, so I define a QTT as follows. So it's a 3 times 3 matrix, and I have here this Q22 transverse traceless here. No? And so this is defined for a general matrix where you have Q11, Q12, and so on. Now it's a little bit of formalism, but I can write this in the form P QP minus 1/2 P trace of P times Q, where this P is a projection orthogonal to the x direction. No? With P is defined as 1 minus, and then you have 1, 0, 0, and you have a lot of zeros here, which is 0, 0, 0, 0, 1, 0, 0, 0, 1. So you see it projects orthogonal to the x direction. So this is a projector orthogonal to x direction. And this now can be generalized to any direction n. So we have then for any direction the projection pi aj is delta ij minus ni aj. So this here will generalize this part here that we have written down for the x direction. So and we define QTT by this general expression with P having this form. Now above we had the following expression for the flux, which was G over 8 pi r squared, and then the trace of Q triple dot transverse traceless squared. And this can now be generalized by using this form to the flux in any direction specified by n. So we have here for this then that we have QKL triple dot QKL triple dot minus 2 QKL triple dot QKN triple dot M, and we have NL and M plus 1/2 QKL triple dot NK and L squared. No? So if you insert this now here, I mean for the general matrix with this projector, then you will get the generalized form of this fx, which was written down earlier with just the Q22 and the Q33 and so on. And you have this expression. You can convince yourself if you reinsert here 1, 0, 0 that you get our earlier expression for the x direction. Now we are slowly approaching the final famous result of this emitted power. And let me define for this the averaged power. The averaged power that is emitted per unit solid angle on the sky and in a certain direction. So averaged power per unit solid angle emitted in the direction n. So power is energy per time. So when I call this here L also because it's a luminosity in astronomy, L gravitational waves. So this is the power emitted per unit angle, and this is the spherical angle omega in a certain direction. And then you see here from it's almost this expression, but the flux is defined as the power per area. And so we have the luminosity without that r squared. So we have here, this is minus g over 8 pi, and then we have this trace of q triple dot gt squared. Now, so that is what we actually have already calculated by having this here. Now, what we are interested finally is the total power, and this is what we also call the gravitational luminosity. So the total power is the gravitational luminosity, and this is obtained by integrating this expression, I mean this, with this inserted over the spherical angle omega. Now, for this to do, we have to use some auxiliary formula for that, which I leave as an exercise, so you look it up, say typically in electrodynamics textbooks you find it. So you have here this integrals 1 over 4 pi integral over the 2 sphere and L and M d omega. This is what you have to calculate here, no? Because you have here these NL and M, and you have here the NK and L and K and L. So you have a bilinear and a quadrilinear term in N that you have to integrate over. So you need to know what that is. And you also need to know what that is. NK and L and M and R d omega. Now, let me first give you the result. So this is 1/3 delta Lm. Now, if you don't know this or you don't look it up, how can you understand that this is correct? Well, you first have to convince yourself that this vanishes if L is not equal to M. And if L is not equal to M, then you have a cancellation from opposite directions. For example, you insert here x times y. Now, if you have linear integral x from minus infinity to infinity is 0. So it must be proportional to delta Lm. But where do you get then this term? Well, you just take L equals M, and or you perform the trace of this, and then you will see that this is just the trace here is 3, and then this is 1, and this here just then gives 4 pi. And in a similar way, you can also calculate this. It's a bit more complicated because it has many deltas, but you can also convince yourself that this is correct by similar arguments. No? You first have to convince yourself that this is 0 for a certain combination, and that only non-zero for this, and then you have to perform traces. Now, if you do that, then you can finally do this integral here, no? Integral d omega, by making use of these integrals over the ends. And what remains are then expressions of the q triple dot. And the result is then, I mean, from these, you then get that L, the total luminosity emitted in the gravitational waves, and I reinsert the speed of light. It's minus g over 5c to the 5, and you have qkl triple dot. I mean, sum over k and l from 1 to 3 and evaluated at retarded time. And this is our end result. So most of what we do now for the rest of this section or even chapter on gravitational wave has to do with that formula, because this is what you get in this linearized approximation, and we will not go beyond. Of course, you can expect that if you have octopoles and so on, that you have octopole contributions, but we will not do that here. And this is the famous quadrupole formula. It's called like that, quadrupole formula. And it was written down for the first time in this way by Einstein himself in 1918. So already in 1916 he discussed this problem, but in this first paper there was a trivial calculational error, so there was a factor wrong. So he extended on this and corrected also that factor, so that's the correct result, and this correct result was first written down by Einstein in 1918, called the quadrupole formula. You remember perhaps from electrodynamics that we often formulate these results in Fourier space, so that instead of temporal derivatives we have powers of the frequency omega, of the angular frequency omega, and also we can do this here. Now if we have the Fourier transform, and so the Qij tilde, which instead of time depends on omega, and we define it here by the factor 1 over 2 pi integral dt Qij of t e to the minus I omega t. Now, so that the inverse here is defined from this without the 2 pi. Now it's not a symmetric formulation. Now we have the emitted power, the total emitted power. Of course, from this you can also calculate the total energy radiated by the source. So the total energy, this is then of course the integral over time, total energy radiated from the source, and so this is E gravitational wave, and I define this as the integral minus infinity to infinity dt L gravitational wave, which if we again set c equals to 1 is minus g over 5, and we have the integral then dt qkl triple dot qkl triple dot. Now we can formulate this with the help of the Fourier transform. So we use that the relation between Qij of t is then the integral of this, so that we can write this as minus 4 pi g over 5, and then we have the integral from 0 to infinity the omega. Then we have omega to the 6. It's clear that you have an omega to the 6 because you have 3 time derivatives twice. So this gives you 6 time derivatives, and in Fourier space this gives you power of 6 in the omega. This is why you have here omega to the 6, and you have here q kl tilde star of omega q tilde kl of omega. So which you can write as the integral from 0 to infinity d omega d e gravitational waves over the omega, and we call this the spectral distribution, because the spectrum, of course, is the extension in the omegas. And this spectral distribution, okay, we directly read off from here, which is then minus 4 pi g over 5, and then we have here this omega to the 6, and then we have here q kl star of omega q kl tilde of omega. I mean, the star is the complex conjugate, and you know that even if this is real, of course, because of the e to the minus I omega t, this here is complex. Yeah, so you see here the spectral distribution is proportional to omega to the 6. For dipole radiation, you would have omega to the 4. No? So dipole would have this omega to the 4. So as you know from electrodynamics, this is this famous omega to the 4 responsible for the blue, well, if it were blue sky that you observe here. But here we have the first term, omega to the 6. So the next thing would be now applications of this formula. And first is an application that we do to two masses that circulate around each other. And I will start with the example where one mass is much smaller than the other, because that's typically what we can apply, say, in the solar system, where, say, the mass of Earth around the Sun, this mass is much smaller than the solar mass. Yeah. Now we make the following application from of the quadrupole formula. So we have two masses, mass m, small m, and the mass capital M, and there is a radius vector r between them, and we have the observer, and so we call this here x small m, and this here x capital M. So r is defined here as x small m minus x capital M. I mean, this is just a flat space vectors because the background is flat. Now we assume here that m is much smaller than capital M. I mean, this is of course a restriction. I could do the general case and I give you the general result later, but this is often employed for in the case of a small body circulating a bigger body. I will not do the full calculation, I will sketch it. You can find it, for example, in Hartl's textbook and in other textbooks, and also in the script when it's ready. So what we have to do here is we have to calculate the quadrupole tensor for that case. No? So we have here, I mean, rho, the energy density that is to be inserted here is of course just the two masses. So it's a capital M, and for the density, of course, we need the delta function. No, recall the delta functions are densities because they're integrated over, and so plus m delta von x minus x m. No? And so you get from this the quadrupole tensor QKL is m x m k. So this after the comma denotes the components xm comma l minus 1/3 delta kl xm squared. This is from the big mass, and then you have the same from the small mass. As I said, I will not now do this in detail. I mean, it turns out to be convenient to put the origin in the center of mass of the two and do the calculation there. And let me also assume that we have a circular orbit in the xy plane. Circular orbit in xy plane. I mean, this has the advantage. I mean, we have R1 is x and R2 is y and R3 is 0 of that R vector here. And we can have we have R is equal to constant, so R squared dot is equal to 0. I mean, this is just for pedagogical purposes in general, and you will see the expression later. We can do it for elliptic motion also. So this results, which is maybe a page or so calculation, then which I leave as an exercise, can be then inserted here. And what we get is then the following. So this here will then be the following: 32. So this expression 32 over 5c to the 5 g to the 4 m to the cube small m squared over r to the 5. That's what you find from this. You may have done similar calculations in electrodynamics or even in mechanics when you apply the quadruple tensor. You can also write this in this following form, so minus c to the 5 over 5g, and you have 2gm over r c squared cube times 2g the small m over r c squared squared. Now, you may perhaps be surprised at first glance about the asymmetry between the masses, m cubed and the small m squared. This comes from this assumption here. Now, the exact result will be symmetric, and you will see it later. Now, why did I write it in that form? Please remember what we did earlier. We in the Newtonian approximation, we introduced the Schwarzschild radius, and we will meet it many times again. So 2gm over c squared. So this here is something like the Schwarzschild radii of the two masses, radii over r. So, and this is a dimensionless quantity, so the dimension is then in this prefactor. And let me give you the dimension of this prefactor. So this is c to the 5 over 5g, which is in CGS units is approximately 7.29 times 10 to the 58 erg per second, or if you prefer SI units, there's a factor of 10 to the 7 between erg per second and watt. So this is 10 to the 51 watt. Now, so this, of course, has a dimension of a power, and it has this value of around 10 to the 51 watt. You can also write this in terms of solar masses or solar energies per second. So this is around 5 times 10 to the 4 m sun c squared per second, which is around 2 times 10 to the 25 solar luminosity in electromagnetic radiation. Of course, you know the sun from emitting electromagnetic radiation, otherwise we would not be able to see outside. And this is what I mean here. No? So this is the solar luminosity in electromagnetic radiation. Okay, by seeing this number, you may say, wow, this is immense. I mean, the emission of gravitational wave leads you to, 10 to the 25 solar luminosities, and you should, see it, of course, everywhere. Well, you have to be careful, no? and of course, the solution to this apparent paradox, because you don't see these powers here as in this factor, the Schwarzschild radius over r. So this is usually tiny, because the Schwarzschild radius is very small. For the sun, only 3 kilometers. So this would only be, say, of order 1 if the objects were very compact. We see that later. This is how gravitational waves were discovered for the first time directly by black holes, which we define later, circulating around each other, and then you can arrive at such numbers or even more. No? So this is an enormous number, but the radii of stars and planets are much bigger than 2 gm over c squared. No? So, which means that you must take into account the numbers coming from this. And you can easily make your own examples. For example, I can, if we have a satellite with 1,000,000 gram, so 1,000 kilogram, a ton, with m around 10 to the 6 gram in a terrestrial orbit, gives around 10 to the minus 35 watt. So you see how this large positive exponents are turned into large negative exponents by this here. I have checked the numbers for the International Space Station, for example. International Space Station, so you find that this has a mass around 455 tons. And it circulates, I mean, you can see it in the night sky by naked eye. So it has a distance from the center of the Earth about 6.8 times 10 to the 8 centimeter. Now that's not the distance, not the height, but to the center of the Earth. And if you put in these numbers, then we find that this is around 10 to the minus 30 watt. So it's bigger than this here, but because it's heavier, basically, but still it's I mean, it's not visible, this power, emitted power. The Earth is more massive, and the Earth moves around the Sun, as you know. So how much power does the Earth emit? Earth around Sun. Of course, you can easily take the parameters from the tables and put this here, and you find that this is around 200 watts. So still 200 watts is, I mean, the order of magnitude of things that you have in the labs of lights. So you might expect to see this, but there's also, as you will see, the problem that the interaction of the waves with detectors is very weak. So also this 200 watt you will not see. So to observe gravitational waves, you really have to find compact objects and in astrophysics, in the universe, so that this becomes large. Now, the emission of gravitational waves, of course, leads to an energy loss, and let us estimate this in a kind of a pseudo-Newtonian approximation. So the emission of gravitational waves leads to energy loss, and so this leads, I mean, if in this case you have these two bodies moving around each other, of course, to a decrease of the orbital radius, no? So they will approach each other if they lose energy, as you know from the Kepler motion. So this will lead to a decrease of the orbital radius r. So in the Newtonian approximation, I mean, we assume that they move very slow, not compared to the speed of light. So in Newtonian approximation for the motion of the body is not for, of course, for the treatment here. Newtonian approximation for bodies. Yeah, so we have, of course, the energy, which is the sum of kinetic energy and potential energy, and you know from the virial theorem of classical mechanics that this is minus v over 2. So then this is v over 2, and this is minus g mm over 2r, no? Because v is minus g mm over r. I mean, we're still for the circular orbits. So from this, also, okay, I had just write this down again. E is minus gm m over 2r. So if by the emission of the gravitational waves the orbit shrinks, so r is time dependent, and the corresponding energy loss can then be expressed as follows: dE over dt is g m m over 2r squared times dr of dt. Now, by energy conservation, this must of course be the same as here. No, I mean, what the body is, I mean, or the motion loses must be in the gravitational waves. So this must be then equal to minus c to the 5 over 5 g to gm over rc squared cube times 2g small m over rc squared. Let me just remark here that if you do the calculation without restricting to small m much bigger than m, then we have the following replacements. So general m, so replace m cube by m squared times m plus m. So this is what comes out for the general motion. And you see then we have a symmetric expression. And we have here the capital M squared, the small m squared, and we have here the sum m plus m, as it must, because if they are arbitrary, you then know one is preferred compared to the other. Now, this is a differential equation for r of t, here of first order. dr of t is a function of r, and of course you can integrate this. So this is a differential equation for r of t, and it leads to the following solution. You can directly convince yourself that r of t is given by a factor r naught that I will write down, and you have 1 minus t over a characteristic time ts to the 1/4. Now this comes from these powers of r that you have here. Okay, the r naught is, say, the initial radius you start with when you count your time, and you see here the characteristic time is the time when this initial radius shrinks to 0. No? So the bodies move around each other, emit gravitational waves, they shrink, and at a finite time they just hit each other. And so this Ts follows from the parameters here, and it's defined by 5 c to the 5 over 265 times g cube times initial radius to the 4th m squared m. Or if you have the general situation, then it would be r0 to the 4th m to the m plus m. So this is the general case. Now, I mean, from classical mechanics, you know that planets and bodies obey Kepler's third law. So we can write it in the form Gm is omega squared r cube. And this is 4 pi squared over t squared times r cube. So you see from this that r dot smaller 0 of course leads to, is connected with t dot smaller 0, so a decrease of the orbital period also. So they move faster around each other. Yeah. So decrease of orbital period. Yeah. So they approach each other and become faster. So this becomes 0 in a finite amount of time. Of course, for very small r, the linear approximation will break down, but for most of the time, the linear approximation is okay. So to get an estimate of the time it takes for the bodies to hit, it's sufficient to use this formula. So should we be worried about, say, stability of the solar system? After all, I mean, we move around the sun and we emit gravitational waves, so at some point then the sun and the earth hit. And in fact, that's true. So stability of a solar system. Now, of course, the biggest planet is the planet Jupiter, with the, biggest in mass. And let us take him as an example. So if you insert here mass of Jupiter and mass of Sun, so you will get a TS of roughly 2 times 5 times 10 to the 23 years. Now, is this big or small time? Well, the age of the universe is around 10 to the 10 years. You will learn that in Relativity 2. So this is of the order of 10 to the 13 times the age of the universe. So you see, you need not be worried about this. So there are much more urgent problems that we face, and even if this is true, it will take very long. But it will be in a finite time. So even if you have no other effects, and there will be other effects, but even without other effects, all the planets will hit the sun in a finite time by the emission of gravitational waves. But of course, we know from stellar evolution that the sun will no longer exist at that time. But there may be a white dwarf then instead of the sun, and it holds for that. So you see, this stability of the solar system is not a cause of immediate worry. So far for this time. So next time we will conclude this section in that we sketch the exact calculation of the phi ij of the metric perturbation and discuss it further, and give also some insight into an indirect test of, indirect observation of the emission of gravitational waves, because this here has been observed, okay, not in the solar system, but for so-called pulsars, neutron stars in the Milky Way that are compact objects. They circulate each other, and one can observe their decrease of the period. And this has been done over many decades already, and found to be in agreement with the Einstein formula. So this we will discuss next time, and also the detection, the direct detection on Earth. So bye bye for today, and until next time.